Hi everybody, welcome back to my channel on Feynman integration. Today we'll be evaluating this integral right here, and I believe based on the form of it, this probably has something to do with the MIT integration bee from 2020, because they often do that. I'm not sure about that, and it was either on the qualifying exam or in the competition itself. I'm not sure. The channel Mathematics MI is where I got this integral from. He evaluates it one way. I'm going to evaluate it using differentiation under the integral sign or Feynman integration. But anyway, I'm going to link to his video in the description. I highly recommend you check out his channel. He has a playlist of about 400 really interesting integrals that I plan on borrowing from and trying to solve them using Feynman integration. But anyway, let's just get right into it. And by the way, the process is going to closely resemble the process I used in another video. You'll see. So what we'll do is we'll consider this function of t. Function of t that is equal to the integral from 0 to 1 of x to the t dt. That's very easy to, that's dx. dx. That's very easy to evaluate. That's just going to be x to the t plus 1 over t plus 1 evaluated from 0 to 1. And that will give us f of t being equal to 1 over t plus 1. All right, well, that doesn't really help us, but let's see what we get if we take f prime of t. If we take f prime of t on this, we'll get f prime of t is equal to the integral from 0 to 1 of x to the t times the natural log of x dx. And that will be equal to negative t plus 1 to the negative 2. This is probably looking familiar to you now. I used this kind of process in developing a integral representation for the factorial function. But anyway, let's take a couple more derivatives and then find the pattern. All right, so f double prime of t would be equal to the derivative of this part with respect to t, and also the derivative of this part with respect to t. So it's the integral from 0 to 1 of the natural log squared times natural log squared of x times x to the t dx, and that is going to be equal to 2 times t plus 1 to the negative 3. All right, take one more, and then that should be sufficient to see the pattern. So f triple prime of t is equal to the derivative of this thing with respect to t, and also the derivative of this thing with respect to t. So that's the integral from 0 to 1 of the natural log cubed of x times x to the t dx, and that is equal to negative 6 t plus 1 to the negative 4. All right, that's good enough for a pattern to emerge. All right, let's take the nth derivative. No. Let's take, I know we're already using t, but there's no reason why we couldn't take the teeth derivative of f of t. I know that doesn't sound right, does it? The teeth derivative. Well, I mean, there's no reason we couldn't do that. So let's figure out what we get if we do that. So if we take the teeth derivative of f of t, that would be equal to the integral from 0 to 1 of, okay, well, this 3 always matches whatever whatever derivative we're on. So this will be the natural log to the tth power of x times x to the t dx. And that will be equal to, well, let's see. We see that it's alternating positive and negative, so we're definitely going to have a -1 to the something power. Well, it matches what, okay, so if this is an even number, then we have positives. If this is an odd number, then we have negative. So it looks like it's, let's see, it's -1 to the t. That's what it'll be, -1 to the t, right? Because if t equals 2, if our tth derivative is the second derivative, then that would be squared, and -1 squared is positive. So yeah, that's correct. Okay, so what's the next part? We have this part, the actual integer there, that will be our t factorial. And then we'll have t plus 1 to the negative t plus 1. Negative t plus 1. Okay. So that's true. If we take t derivatives of this function, if we take t derivatives of this function, this is what we get. That the tth derivative of f to the t is equal to the integral from 0 to 1 of this, which is also equal to this. All right, so let's see. This is almost what we want, except we just have to plug in 2020 for t to get our answer. So let's not plug it into this one, let's plug it into this one. So let's see, that would give us -1 times to the 20/20th power times 2020 factorial, and then we'll put this over this to the positive that. So that would be, let's see, t plus 1 in this case is 2021. And then that will be to the 2021 power. And that is extremely close to 0, actually. It's not quite 0. As you can see, it's not 0, but it's very close. And you'll also see that since this is an even power, that will just become a +1. So we can just write it like this. So that's it. That's what the answer is. I know it wasn't. This is not appropriate notation. I really should have done the nth derivative and then plugged in t for n to get that. But this was more direct, and it gets the job done. That is the answer. I checked it. It matches up with what Mathematics MI, his answer is. So anyway, there you go. There's that MIT Integration B problem solved using Feynman integration. Hope you enjoyed that.